on the electromagnetic radiation, the photons that we see streamed outward, right? So we can use this measurements, this data, to actually look back in time. Now, we physicists, when we look at something like this, we have ways of thinking about it, but you can actually don't have to be a physicist to look at this and say, that's not completely random, right? There's some structure here, right? There's, a cold spot here, there's, structure with the hot spots, and in fact, you can just look at it and see that there's somehow characteristic sizes, right, for these variations, right? And so when physicists see something like this, what we try to do is ask questions like, all right, if I took this and asked, what contribution is there from things that vary really slowly, right, as we look across the night sky, and how much contribution is there things from very, very quickly, right, then we might imagine making a spectrum, right, of the different contributions. Now, to give you some analogy, right, I want to take a break here for just a second, not even an analogy, I'll give you a direct demonstration. Let's see if I can pull up my sound meter. I have just a Fourier deconvolutor Fourier analyzer, right, that just takes sound waves and breaks it up into its frequency spectrum, right? So what's being shown here as I speak are low frequency, so low, high, and the problem is my voice doesn't have much range on this scale, so it all kind of looks the same, but yeah, right? So what we're doing here is just taking sound waves, right, that vary as a function of time, and we're breaking it up into the parts that vary really slowly, that's low, right, and the parts that vary really rapidly, that's high, right? And here you see a spectrum of different components, low frequency and high frequency, okay? Well, this is what we do also when we analyze the data from the cosmic microwave background, okay? We break it up into components according to basically low frequency, that's down here, and high frequency up here, right? So essentially we do a frequency decomposition of that angular distribution, right? We say, what features there correspond to components that vary slowly, and what contributions are there from features that vary very quickly? And you notice this is not uninteresting, right? It actually has some complicated structure, right? And I'm not going to try to go into that structure, but the amazing thing is that basically these measurements and our ability to understand them, this red curve is essentially a model fit to the data, where that model is our best understanding of how the cosmology of the early universe works, right? We can take this fit and extract information about the universe at a level of precision that was unimaginable when I was a graduate student, right? When I was a graduate student, we didn't know whether the universe was 7 billion years old or 15 billion. So I want to go on to something that's a little bit different. There's another way to look back in time, which is actually to do the analog of what we do when we look back in time in the universe, right? Which is to look at the look as a function of angle and see what we see. But remember what I said about these collisions kind of being different from the universe in that there's a special direction, the direction of the beams. And what we do is we look in the angle, right, in the plane perpendicular to the beam. So here's an event. It's actually from a different experiment, but it's kind of a nice demonstration. These are tracks of particles. They bend in a magnetic field. What we do is we basically plot as a function of the azimuthal angle, right, the angle in the beam perpendicular, in the plane perpendicular to the beam, how many particles we see. So here's such an event. Okay? How many particles we see? Well, we see more there, less there, more there, less there, more there. And this is really weird because in normal particle physics, except when you have jets and the jets produce concentrated sets of particles, you don't see this. Okay? So there's something that's breaking kind of the natural symmetry of collisions that is actually causing more particles in one direction in the plane than the other. Well, in fact, we even knew that this might happen as as well, because what happens is nuclei are extended objects, and when they collide, they don't necessarily collide head-on. Sometimes they collide, I meant to bring in my son's soccer balls to show you this, but I forgot them. So sometimes they collide like just grazing, and then sometimes they collide head-on, right? And when they collide somewhere in between, right, then what happens is the nuclei shear kind of a piece off each other that is sort of oblong, right? It's longer in one direction than the other. And the thing is, if we're creating a hot plasma and it's developing a lot of pressure, when you have such an oblong system, it pushes more in this direction than it does in this direction, right? Basically, the effect of the pressure is to cause it to explode this way. Now, I'll show you a different system that behaves like this in a couple minutes, but that produces this modulation. So this sort of non-uniformity in angle, which is actually not so radically different from the non-uniformity in angle we see when we look back in the universe, except this is a very slow modulation, is due to kind of simple geometry. But, and this was a surprise, and I'll say more about this in a minute or two, the size of this effect was much, much bigger than expected. Now, however, that was averaged over many, or put this way, we tend to see these things, especially this modulation, if we average over many events. This event, this is actually one event. It tends to be relatively simple, but we see events with much more complicated modulation. So we see events that look like this, or this, or this, where this is the number of particles as a function of angle in the plane perpendicular to the beams. And now you see there's not just, well, this is almost perfectly single sinusoidal modulation. You see much, much more complicated structure. And if you allowed yourself to, collapse from 2 dimensions, looking out into the universe, right, and that picture I showed you is a function of angle, you can look all the way in different directions in the sky, just collapse it down to 1 dimension where there's 1 angle, right? This is actually quite analogous. We're seeing complicated variations in the number of particles, not the temperature, but related to the temperature as a function of angle. And we can actually do the frequency decomposition. And if we do the frequency decomposition, we can do it for particles of different momenta. So in fact, these are different slices for different momenta. We see something which we have less statistical power, and the range that we can do in essentially frequency is more limited, but actually something that looks a lot like what we saw when we looked at the frequency decomposition of the early universe. And in fact, you could ask, where do these come from? Well, actually, we know where they come from. They come from fluctuations in the energy density or the temperature in the initial state of the collision, right? So if you think about these collisions, and remember I said one direction is special, right? At the initial state, you can think of where is the temperature or the energy right at the very beginning in the plane perpendicular to the beam. So this is like the XY plane. The beams are coming this way. It's or maybe the beams are coming this way. The plane of the board is the XY plane. And the temperature doesn't have to be uniform right at early times. Okay? So it can actually fluctuate, and the colors here represent red is higher temperature, blue is lower temperature. These are 3 different models because we don't understand this physics perfectly well. In fact, there's a lot we don't understand, but 3 different ways of trying to describe what's going on. They all show significant fluctuations. Right? So remember how I said in the early universe, quantum fluctuations get stretched by the expansion of the universe into this angular distribution of the cosmic microwave background. Well, what I'm going to tell you is that these initial quantum fluctuations, because they really are quantum origin, in the initial state of heavy ion collisions get stretched by later evolution to be the angular distribution of particles. And how do we understand that stretching? How do we understand the evolution from the initial state to the final state? Well, we actually have a tool that